So our next lecture will be given by Dr. Stanley Whittingham. And Dr. Stanley Whittingham was born, as you can see, in 1941 in Nottingham in the UK. And he earned his doctoral degree in 1968 from Oxford University in UK. And after his doctoral degree, he moved over to the US and to Stanford. And later on, he stayed on in the US after his postdoc, in part for family reasons. And he moved to Exxon Corporation in the beginning of the 1970s. And later on, he came back to academia, and he's now a distinguished professor at Binghamton University, part of the State University of New York in the US. And he's also a director of the Northeast Center for Chemical Energy Storage. So please join me in welcoming Dr. Whittingham up on stage.
Thank you very much for the introduction. Good morning, ladies and gentlemen. What I'd like to do is give you a little bit of the history, my history, and the history of electrochemistry. And on this first slide, I show you the folks that essentially trained me, helped me, and hopefully I gave a little bit back to them. Let's start at the very beginning. Volta, in about 1799, really built the first battery. And in return for that, he got his temple. Very nice prize. That was pre-Nobel times. And this is Lake Como in the background. If you go to the other side of his temple, you'll see the Alps covered in snow even in July. And on the right-hand side is really Michael Faraday, who was the father of electrochemistry. He gave us the foundations of electrochemistry. And he was based in London. But starting with me, you get into science because certain people get you enthralled and excited about it. And I went to a school in England. This is Stamford School. This is a school here. Okay? And I had two great teachers. Major Lamb, who taught me chemistry, and Squibs Bowman, whose pictures I've got here, who taught me physics. And one thing, putting this talk together, I found out very quickly, people didn't take many photographs in those days. It was very difficult to find photographs. But the school found in their archives, these are my teachers, and this was in 1960 when I graduated. And this is Squibs Bowman, this is Major Lamb, and here is the headmaster who played a key role because I got accepted into Oxford, but to get into Oxford you had to pass Latin. And he mentored me in Latin so I could get into Oxford and do chemistry there. So two other people played a key role in my scientific life. Peter Dickens was my advisor at Oxford, and unfortunately he passed away just 1 week before this prize was announced. And then at Stanford, Bob Huggins was my mentor, and here I was in inorganic chemistry. And as you heard in the previous talk, interdisciplinary research is critical. Metallurgy was part of inorganic chemistry at Oxford. And Hugh Roddery taught me metallurgy. Okay. And then I went to Stanford into the materials science and engineering department as a postdoc and then a research associate. And as mentioned in the introduction, that's where I met my wife and our two children, and the 4 grandchildren are all native Californians. So let's look a little bit about why I got involved and how really did the battery effort begin. And it began at Oxford, and it began looking at what we call tungsten bronzes. These are bright metallic materials, metallic conductors, and we showed that they showed very fast ion transport, and that was then going to become critical for battery research. And you can see here are 2 structures. These are tunnel structures, 3-sided tunnels, 5-sided tunnels, square tunnels, so we could design the transport for the ions depending on which tunnels they sat in. And here is one, the simple perovskite, all square tunnels. So we looked at these materials initially as catalysts, Some of you may remember this was a Sputnik era. There's a lot of interest in fundamental research, and this work was in fact paid for by the United States Air Force from their London office. And then I went on to my doctorate, so we then looked at these same materials for the ion transport properties. Initially, I was supposed to be looking at them for catalysts to convert coal gas to natural gas. But some of you older folks may remember in the summer, when I finished this 65, 66, Britain struck natural gas in the North Sea. So the Gas Council said, we're no longer interested in this research. Do whatever you want, you've still got the money. And don't bother reporting to us, okay? So we studied the transport behavior in these materials, and then when I went to Bob Hunger's lab, we actually did the thermodynamic behavior of how we synthesize these materials using electrochemical means. But there was a significant breakthrough. I went in '68. The previous year, researchers at the Ford Motor Company had discovered the fast ion transport in sodium beta alumina, showed that sodium ions in this material move just as fast as sodium ions in water. And Bob and I presented a paper on this, and this is the title we gave to it. We didn't really predict it was going to be that great, but clearly this material is the one that started off the whole battery revolution in solids. And the Ford folks proposed sodium-sulfur batteries. This led to a search for other high ionic conductors. And John Goodenough started working on NASACON to try to find alternatives to beta alumina. Let's look at what is special about beta alumina. And there's some big names here. This is a layered structure. So 4 layers of oxygen in this very open structure, another 4 layers, very open structure. For many decades, this was considered to be just aluminum oxide. But it was Linus Pauling who worked out, said this material's got sodium in it, and it's the sodium ions that set in these layers, and I've shown them here in red. Okay? And what we found out later, this material has about 15% excess of these ions, and that's what lets the ions move very, very fast. But then came the real challenge. How do we measure how fast these ions move? You can't just put regular electrodes on because they're moving too fast. So we went back to our tungsten bronzes. So here we have the same tungsten bronzes, whether the tungsten or vanadium ones. These are mixed metallic conductors. So if you want to measure ionic conductivity, you've got to have electrodes that move both electrons and ions. So we built up a simple cell here, tungsten oxide electrodes, then in the middle here, single crystals of this beta alumina. And then we could measure the conductivity over this range, is about -180 to 800 degrees centigrade. So single mechanism of over that whole period here. And the key thing here, if you look at this carefully, this is really a battery. We have sodium tungsten oxide on this side, same on this side, and we could pump sodium backwards and forwards. So this was really the first solid-state battery. What is important at this time, this was 1972. If you looked at the literature and tried to understand what battery chemists thought was going on, none of them really realized that you could form ternary phases. There was no thought of insertion reactions, intercalation reactions. So if you look in the literature, vanadium pentoxide would react to give vanadium 2O4, so you abstract oxygen here. Your standard alkaline cell is presumed at that time, you again abstracted oxygen and form Mn2O3. Most solid-state chemists will say that's not going to happen at room temperature. It doesn't make sense. So what in fact happens in these cases, you get lithium ions inserting into this one, and you get protons going into the manganese oxide, forming manganese oxyhydroxide. And this really led to the whole concept of intercalation chemistry within battery materials. So, and we just published this in 1976. So let me briefly describe what intercalation is. If you get an old dictionary, let's say from the 70s or 80s, this is what it will say. Intercalation is putting February the 29th into the calendar every fourth year, then you take it back out. And if you actually go and look at the older dictionaries, they in fact say Romans couldn't count how many days there were in the year, so they had to eventually intercalate January and February into the calendar. Okay. If you now look into the dictionaries, intercalation, they now talk chemistry. So they talk about intercalation is the insertion of ions, guest species into some host lattice. So that is a generally accepted definition now, and this means reversible. If we're talking about these, we're talking about either molecules or ions can get inserted, and your host materials can be inorganic. And when we first published this book in 1982, I think it's one of the first papers that actually talk about the intercalation of drugs into the helixes of DNA and materials like that. Let me briefly talk about TiS2. Ram did a great job of introducing it, so I can jump over this fairly quickly. But we've got a layered structure like TiS2. If you look at this, it's about 5.7 angstroms. You put lithium in, it expands by half an angstrom. So this are the ions going in here, and then you've got the electronic structure. The valence band is full, so the electrons then start filling into the conduction band. Clearly, as you fill this up, then the voltage you're going to get out of the cell drops somewhat. But there are some key aspects of this material that I want to show you. Here's TiS2. It has a layered structure exactly like this, exactly the same as cobalt oxide. Here are the lithium ions, and this would be TiS2. This is a semi-metal. Now, I just call it a metallic conductor, so it's a very, very good electronic conductor. So you don't have to mix any carbon like you do in most materials. And this is a typical discharge curve. It goes down because we're filling the conduction band up. Then when you recharge, you follow exactly the same curve. And this is just the resistance of the electrolyte. And this is data from 1973. And this is the 76th cycle at that time. And for the younger folks in the audience, we had to build all our cyclers ourselves. There were no such things on the market. And everything was chart recorders, so you had to measure everything from paper. There's no nice computers in those days. Okay. And the other key thing I point out, because this is a good conductor, we got current densities of 10 milliamps per square centimeter. Typically, today it's about 1. Okay. So this was an ideal cathode, except for one thing. The voltage was a bit too low. And so we didn't need any carbon black in there, and there's no phase transition. So this is a single phase all the way. I should thank at this point some far-sighted companies. It was then Esso. It went to Exxon, and now is Exxon Mobil. They were willing to invest in this technology. They were an oil company that wanted to be an energy company. And we started this work, in fact, before the energy crisis started in 73 and 74. But then they put money into this for the next 2 decades. So this is a titanium disulfide. It's a metallic conductor, so we can use large plates of it. You don't have to use very fine powders. And this was me just a few years ago. Okay. And you'll notice now, lapels are wider, ties are wider than they are now. So men's attire does change with time. Let me just show again the slide you saw a little bit earlier. This is a typical intercalation battery. I say it's 70s technology. Absolutely nothing's changed in the mechanism. Every lithium battery you buy today is the same way. So you're intercalating lithium ions into a host over here, and you have a host on this side now. This is typically carbon-based. This is Yoshino's invention, and all you're doing is shuttling lithium ions from one side to the other side, and back again. If you have lithium metal in a lithium ion battery, you've got problems. So the whole goal here is not to have any lithium metal. So initially we started with pure lithium metal at Exxon. We then switched to aluminum for safety reasons, as you've seen before, and then Dr. Yoshino went to carbon, and I'll talk about this in a moment. But let's just look a little bit of the history here. This is a paperweight that Exxon made. This is about 1976, I think. This is the battery, little solar cell, a watch here. This particular one still sits on my desk. 40 plus years later, it still works. So a well-made lithium battery will last essentially forever. Okay? And this is a larger battery. This is about 6 inches by 4 inches by about an inch thick. These were batteries made for electric vehicle show back in 1977. And these just sat on the bench top. And these turned on a motorcycle headlamp on and off all week long with no problems. Those of you who are chefs will notice some pressure release valves on top. So each night after all the people had left the building, we would then release the pressure inside them because we had some boron ether electrolytes in there. But no, these worked exceptionally well. The other point I want to make, I've been working on and off with John, I think, since 1977 when we organized a big energy meeting in New York City for the American Chemical Society. And John and I are still working together on this Battery 500 consortium. So we've got a few years' efforts between us. But let me go through a few things on this side. So it's the 1970s when we did TIS2. Then a few years later, there's a lot of work coming out of British Columbia, Vancouver, because in Vancouver they have molybdenite as a natural ore, so they dug this out of the ground as being a more environmentally satisfactory and built batteries of this. And this went commercial for about 5 or 6 years until they had some safety issues with it. But this used pure lithium. Then John developed the lithium cobalt oxide. Then Yoshino came up with the coke. And then it was really Sony who built, I would say, the economically successful batteries that then went into camcorders and other events and really got the electronic revolution going. And I can put this in a slightly different format on this slide. Here's where Exxon started out, went to lithium aluminum, then Yoshino's effort took us to carbon, and this is where we basically are today. We still use carbon as the anode. There's a lot of effort now, though, to try to switch to modify the carbon by putting tin of silicon on it or pure materials, and a lot of effort now to go back to pure lithium now that we have tools to really understand what's going on. Similarly, on the cathode side, we started with titanium disulfide, then went to cobalt oxide, and then in this intermediate period, people started changing out the cobalt and mixing it with nickel, manganese, and aluminum. So in there now we're going to have a whole range of different transition metal oxides. Then as mentioned, John came up with the olefins, the lithium iron phosphate, and I'll talk briefly, we've now come up with what we think is the next generation, where we can now stuff 2 lithium ions into the same structure and hopefully get higher energy densities. Now, one comment I've got from a number of people, okay, you've got the Nobel Prize, that means we don't have to do any more research on lithium batteries, it's all done. I have to remind them, no, we're not close to that. So if you look at what we get out of a lithium battery, we only get 25% of the theoretical energy density is in the practical cells. So there's a huge opportunity for us to move forward. One area where there's a lot of work now is to modify the carbon, because the carbon takes up half the volume of the cell. So we want to modify that. We need to get higher lithium contents, because right now the layered oxides, like lithium cobalt oxide, we only use 60 to 70% of the lithium. And then the big issue is, instead of just having 1 lithium per metal, can we push that to 2 lithium per metal? Okay. And we really need to do more fundamental research. We need to get those ions to move faster. We need to get electrons to move faster. Then we can make thicker electrodes, reduce the number of current collectors, separators, and all the dead weight within the battery. So these are the layered oxide materials we're looking at. These are some of the phosphate tunnel structures we're looking at. And I want to give you just a couple of examples of where there's still opportunities in the future, even on materials that are 30, 40 years old. So let's look at the layered oxide materials first, these materials. What we find out when we charge these materials on the very first cycle, so here we charge this material, this is an 80% nickel material, charge it up, we lose 30 milliamp hours per gram. That's about 15% of the capacity on the very first cycle, and we never get it back. So we've been trying to find out what's the reason for this and how do we solve this. So we've been doing some basic research there, and what we find out is it's the fundamental behavior of these materials, really how fast do these lithium ions move or how fast they don't move. So you can see here, don't worry about the numbers here. This is how fast they move. Then once you get to about 80% lithium in there, this drops off by 4 orders of magnitude. So a huge drop off in the diffusion coefficient. So we're right now studying how can we solve this problem so we can get this last part of the lithium in. And if we do that, we can get these materials up to about 400 watt hours per kilogram. Today's batteries are about 250. So there's a huge incentive that we can go there. Similarly, we started looking at can we stuff 2 lithium ions or 2 sodium ions into many of these structures. And we looked at vanadium compounds, because vanadium can go from 5+ to 4+. And we had students working on this for many years, and they found out we made these little cuboids. These are about 100 to 200 nanometers in size, and you do it the right way, so the synthesis is critical. And here, I'll take the point of thanking all the students and postdocs who took all the time. And people say, why do you do science? Because when you got a success, it's really gratifying, but there's many hurdles you have to get over before that success came. So there are 4 or 5 students working on this before we succeeded. And this is then cycling curves again. 1 plateau up here and 1 down here. And this is 50 cycles. And in fact, this material behaves better on the 50th cycle than on the first one. So we had proof of concept that we could, in fact, put 2 lithium ions into a crystalline lattice and intercalate in there without destroying that lattice. And that was critical. So now we can move on and see if we can do even better. But what I want to close on is to make a few general comments. No, lithium batteries are now dominant. I think in dollar science, no, lead acid may still have more, but there's nothing matching lithium ion. And I want to give a few examples here. My wife's in the audience. She will tell you that range anxiety is real. So this is a little car, and you notice she matched the sweater to the wheels on the car. So everything is, but this is a little car we rented in Bermuda for our 50th anniversary. And what they warned us when we picked it up, if you go to the far end of the island, you won't be able to get all the way back. So we went to the far end of the island. They said there's a charging station there. We got there. Yes, there was a charging station there. They were still building it, though. So part way back, we found this other charging station. We left it there for about an hour, and it gave us enough energy. We had dinner, I think, in the meantime, enough energy. So by the time we went back to our hotel, it started beeping wildly with 3 miles to go, saying I'm out of electricity, but it still made it. So this is a key issue. And you all know about electric transportation. This is the Jaguar. And BAE Systems, which has an office in Binghamton, is where they make all the power systems and all the batteries for electric buses. They support the electric buses in London as well as in Binghamton. And the United States, Binghamton has the largest percentage of electric vehicles in their fleet of any town within the US. Okay. These are little systems. Just 2 weeks ago, I was just north of Seattle at a truck company. And this is a truck, and these are lithium-ion batteries. So this is what we call a 16-wheeler, a big truck. And this is the test tracks where they let us drive these trucks around. The test track, and the only comment was, don't go above 50 miles an hour, please. So we went around the track. But these are extremely powerful. They're very clean. And where they're testing these out now are in dockyards, where the trip is maybe 20, 25 miles to pick up the big trailers and ship them to the next shipping point. They're also making these garbage trucks. And it was what my daughter said, I want a picture of you of a Nobel laureate driving a garbage truck. But again, this is an all-electric truck, and this is a perfect scenario for electric vehicles. It stop, go, the entire time. Lifting garbage cans up and down, so you've got regenerative energy in those cases. But as mentioned in the previous talk, batteries are really enabling the renewable energy situation. And this is the sunshine. We all know the sun shines when it pleases, and that looks like Stockholm. It's just like Binghamton. It doesn't come out too much in the winter. Okay. System here, this is a wind farm in West Virginia, and I think this is about 24 megawatt hours of batteries. They use this to both smooth the wind farm and to shift the load to when it's really needed. And on the right-hand side here, this is a system. We took this picture in August this year, just south of Saratoga Springs in New York, next to two utility stations. And this one is already making money. They buy the electricity when it's cheap and sell it back to the utility when it's more expensive. And the comment there, when we looked at it and said, how much maintenance is there on this? They said the biggest maintenance is mowing the grass around the fence. So they don't visit this facility more than once every few weeks. It's controlled from a distance. Down here is a 4 megawatt system that used to be in Binghamton. And it was in Binghamton for about 4 years. After 2 months in Binghamton, they closed down permanently a neighboring coal power plant. So this is where a lithium storage facility can really clean up the environment. Okay. And I don't need to discuss this. I think everybody has one or more lithium batteries in their pocket somewhere. But what energy storage is going to enable is renewable energy. It's going to make it cleaner, more sustainable, and it's going to allow us to mitigate global warming, which I would say these days, I call it more global messing up, because you get more cold periods, more hot periods, it's all mixed together. And it's going to give us a more efficient grid. And I will stop there. Thank you all for listening, and thank you for the Nobel